In the present video, Electrostatics Part 4, we will be studying about an important concept in nature, the electric dipole and the dipole field. Basically, electric dipole is a special system of charges. A pair of equal and opposite charges placed a certain distance apart is said to constitute an electric dipole. As you can see in this diagram, we have a charge minus q and plus q separated by a distance 2a. The distance is mentioned as taken as 2a for mathematical convenience. So such a system of charges plus q minus q held a certain distance apart is said to constitute a dipole. For a dipole, we define another term, electric dipole moment, denoted by P, is the product of either of the two charges, because both are equal in magnitude, and the distance between them. So mathematically, you can write dipole moment P equal to Q into 2A. The electric dipole moment is a vector quantity, and by convention we take its direction from negative towards positive, negative to positive. The SI unit is unit of charge into unit of distance, that is coulomb meter. The dipoles are important because they occur too frequently in nature. Example, in a sodium chloride molecule, sodium being a metal loses its electron, therefore the electron is transferred from sodium to chlorine. Sodium acts as seat of positive charge and chlorine the seat of negative charge. So sodium chloride molecule is an electric dipole. Now the line joining the charges of the dipole, that is this line AB, is called axial line of the dipole, and the perpendicular bisector of AB is known as the equatorial line. Now coming to dipole field, let's first find out the field on the axial line of the dipole. Consider a point P at a distance r from the midpoint O of the dipole. We will calculate the field at this point P. Clearly the point P will have electric field due to positive charge as well as due to negative charge. So net field will be superposition of the two fields. The electric field intensity at P due to positive charge is given by EPB. Field at P due to charge at B equal to E1 or Q over 4 pi epsilon naught 1 over Bp square, that is Q over 4 pi epsilon naught 1 over r minus a whole square along PL, because the field is always directed away from the positive charge towards right. Similarly, field at P due to charge at A will be directed towards left and will be given by Q over 4 pi epsilon naught 1 over AP square. AP from the diagram you can see is R plus A, R OP plus OA, so R plus A whole square along PM directed towards the negative charge. Since E1 in magnitude is greater than E2, so we will get net field at P equal to E1 minus E2. E1 dominates, as stated earlier. The denominator r minus a is smaller than this denominator r plus a. Net field is along PL. Q over 4 pi epsilon naught is common, and then you can simplify this expression to get Q into 4AR over r square minus a square whole square. This 4a you can write as 2 into 2a. So Q into 2A, you can use this definition of dipole moment, that gives you 2pr over 4 pi epsilon naught r square minus a square whole square. Now if you see, the net direction is along PL and the dipole is also towards right. Dipole moment is from negative to positive towards right. So the field direction PL and the dipole moment have same direction. So we take P as vector here, which takes care of the direction of the net field at P. Net field due to dipole on axial line is given by 1 over 4 pi epsilon naught 2pr over r square minus a square whole square. In a special case, if the dipole is short and the point P is far off, then we have R very large as compared to A. So we can neglect A as compared to R. So denominator will be R4. R will cancel out. You will be left with EP is equal to 1 over 4 pi epsilon naught 2P over R cube. Now for dipole field on equatorial line, let's consider a dipole with charges plus q minus q separated by a distance 2a as shown. P is a point on equatorial line of the dipole at a distance r from O. Now once again, the net field at P will be a superposition of field due to minus q charge and that due to plus q charge. So we have field at P due to A. If we call it E1, it is q over 4 pi epsilon naught 1 over square of the distance, that is AP square. By Pythagoras theorem, AP square is R square plus A square. So the field E1 is q over 4 pi epsilon naught R square plus E square along PL because it is directed towards the negative charge. Similarly, field E2 due to the second charge at B, EPB, will be q over this square, that is 1 over 4 pi epsilon naught q over r square plus a square, which is also PV square along PM away from this positive charge. Net field at P is the vector sum of the two fields due to individual charges E1 and E2. In order to calculate EP, let us resolve E1 and E2 along horizontal, that is parallel to AB, and vertical along R. The components of E1 are E1 cos theta along horizontal or along PN and E1 sin theta vertically downward. Similarly, components of E2 are E2 cos theta along PN and E2 sin theta vertically upwards. So the components are E1 cos theta along PN and E1 sin theta vertically downward. Similarly, E2 cos theta along PN and E2 sin theta vertically upwards. The components E2 sin theta and E1 sin theta, they are equal and opposite, hence these vertical components cancel out. The horizontal components E1 sin theta is along PN and E2 sin theta is also in the same direction. So the horizontal components will add up. So net field at P is given by E1 cos theta plus E2 cos theta, and since E1 is numerically equal to E2, we get net field as 2E1 cos theta. Substituting for E1, you get this expression, and cos theta from the diagram is OA over AP. That is, OA means A over R square plus A square root along PN. This is the direction of the net field. So overall the result is Q into 2A, which is P, the dipole moment, and we attach a negative sign because the dipole is from negative to positive. Dipole moment is negative to positive along AB, and the field is in opposite direction. Hence E and dipole moment are in opposite direction, introducing this negative sign over r square plus a square 3 by 2. Taking a special case for a short dipole at a far off point, that is r very large as compared to a, we neglect a as compared to r. That gives you r square to the power 3 by 2, which is r cube. So EP is minus P over 4 pi epsilon naught r cube for a short dipole. If you compare the equatorial field and axial field for a given value of r, same r, the field on the axial line will be equal to twice the field on equatorial line. Numerically, this will be the relation for same dipole, same value of r. Having studied the dipole, let's now see how will a dipole behave in a uniform electric field. For the purpose, let's consider a dipole with charges plus q minus q separated by a distance 2a in a uniform electric field of intensity capital E. These are the two charges of the dipole. Force on charge at A, that is this negative q charge, will be minus q into E by definition of the field. The force is QE opposite to the field because the charge is negative. Similarly, force on positive charge at B will be plus QE or QE along the direction of the field, along the field opposite to the field. The two forces are equal but opposite, therefore net force is 0. The dipole will not show any translatory motion if it is placed in a uniform electric field. However, the forces being equal, unlike and opposite, equal, unlike, right, left, they form a couple. The moment of the couple is given by either of the forces multiplied by perpendicular distance. Either of the forces because the two are equal. So the force QE into perpendicular distance between the forces, that is BC. QE into BC. BC is AB sine theta, as you can see from the diagram, or 2A sine theta. So you can combine Q and 2A, the product is P. So the torque tau is PE sine theta. This is moment of the couple experienced by the dipole in uniform electric field. Or vectorially you can write tau equal to P cross E. Remember, the direction of the torque is given by cross product rule as applied to P cross E. Here the torque tau will always be perpendicular to P and it will also be perpendicular to E. This is by cross product rule applied to P cross E, or that is the right hand rule applied to P cross E. The torque is 0 when theta is 0, that is P is parallel to E, or P anti-parallel to E, that is theta is 180 degree. And the torque becomes maximum when the dipole moment is perpendicular to E. The maximum value of torque will be P into E and minimum will be 0. It's important to remember that torque will be perpendicular to P and it will also be perpendicular to E. That is, in this expression there are two pairs of perpendicular vectors, torque and P, tau and E. Now let's see the energy of the dipole in uniform electric field. If the dipole makes an angle theta with the field direction, the torque experienced is given by Pe sin theta, the magnitude of the torque. If you rotate the dipole from its present position, that is angle theta, through small angle d theta, that is 2 theta plus d theta, the work done for rotation is given by dw is equal to tau d theta or Pe sin theta d theta. And work done for a rotation from theta 1 to theta 2 is given by the integration of this expression Pe sin theta d theta. P and E being constants, you can take it out, and integrating you get this result within limits theta 1 to theta 2, you get this expression. The work also measures the change in potential energy of the dipole. For numerical value of the potential energy, the reference level in this case is taken as 90 degree. That is, we measure potential energy of the dipole with respect to the dipole being perpendicular to the field. So putting theta 1 equal to 90 and theta 2 equal to theta, some general value of theta, the result for potential energy or expression for potential energy is minus Pe cos theta equal to minus P dot E. This is dot product of P and E. Now there are some special cases. If you take theta equal to 180 degree, cos 180 will be minus 1 and the potential energy will be maximum. Now we know that in this case the force on the dipole is 0 and the torque is also 0, therefore it is in equilibrium. But since the energy is maximum, the equilibrium is unstable equilibrium. For dipole parallel to the field, theta is 0 and the energy becomes minus Pe. The equilibrium in this case is stable equilibrium. If the dipole is in a non-uniform electric field, that is, the field intensity at this point and this point they are different, then one of the two forces will be larger in magnitude and the net force on the dipole will be non-zero. In such a case, the dipole will experience a net non-zero force as well as a torque, resulting in both linear motion as well as rotational motion.